And here we go.
You're live?
I think we are live. I hope we are live.
Yeah, I
Hello,
can see us.
everyone. I think.
Hi, hi guys.
Can you guys hear us all right? This is a bit of a new setup. Ah, awesome.
Stay home, stay safe.
Oh yeah,
That's right.
we're staying home. These are fake backdrops, just photos from the office.
It's our virtual office.
So yeah, guys, it's good to be back. We're gonna try to do this online, so the quality might go down suddenly, or we might drop off completely. So
Yeah,
let's see how this goes. But yeah, we're working from home as we said before, and we're trying to stay safe. But we still want to give you some insights. And Paulo has prepared something really cool that we got asked a lot. So do you want to elaborate on that, Paulo?
yeah. So today I actually have prepared to you a bunch of shaders that mention the topic of normal reconstruction. You would actually do this, or you need to do this whenever you do like a vertex modification shader. So you have like maybe you want to do like a sand effect or a snow effect, and you need to displace the vertices. And sometimes you get these weird looking lighting when you use that technique.
Yeah.
And you need the reason for that is because the normals were not updated accordingly. So you need to reconstruct them. So that's for what we are going to talk today.
Awesome. I think many users will find that useful. Just a quick reminder, we're also part of the spring sale. I have to mention that.
Yeah.
So yeah, if you're looking to get our editor or Amplify imposters for optimization, you can get them now at 50% off. It's going to be a while. It's going to be around for a couple of weeks, I think. So take your time. Ask us anything about the products you might need to know, and we'll get back to you. Preferably on Discord, because we're always online. But yeah, I think that's pretty much it. So do you want to jump right into sharing the screen, and hopefully everything will work?
just checking the chat first.
Any questions there?
Uh,
Let's see.
in the other shader, in which order the shader process the vertex. Not sure if I'm understanding, Patrick, the question. So what we are going to talk today is, well, let me start sharing the screen. Maybe you can catch up on that question. So I'm going to share my screen.
Go for it. Hopefully it shares the right screen. Should be fine. Are you sharing? Oh, there we go.
Yeah.
Okay.
Okay.
Cool. Wow, it worked. Yay. I'm just going to move
Okay.
our screen.
Not the part. Okay. Okay. So you should be seeing my screen now.
Yep.
And what I'm going to talk about is, for example, here I have the one of the samples that we share with our package, which is those sand textures. Like they have the albedo normals and whatnot. And here I have a plane where I'm displacing the vertices using the height map of that sand. And you can see that even though we did displace the vertices, I'm going to turn on the shaded wireframe mode. You can see that the vertices are being displaced correctly, but the lighting is all weird. So this happens because when you do this kind of vertex modification, you are only just changing the position of the vertices around. You're not actually doing anything else. So for the shader, which uses the normals to calculate lighting, basically you still have the old lighting. So for example, if I now take off the displacement, you can see this is the perfectly clear plane.
Yep.
And that's why when we do the displacement, it still stays the lighting still stays the same. So the only thing you are seeing right now is these black parts here, or darker parts here. They come from the actual shadow mapping. So what happens is that at some point they get so steep that the shadow mapping starts to kick in and starts producing shadows. But besides that, you don't have any kind kind of modification to the lighting. So what we are going to do is I'm going to present some, let's say, fast solutions. So if you have like just a quick case that you want to change or want to fix, like this one, for example, and then I'm going to share some more solutions for more complex cases. So let's try to create a shader from scratch like we usually do. I'm going to create a new shader. By the way, I'm using the built-in renderer only because it's easier to show with the tessellation. We are still working on bringing tessellation to the scripting running pipeline, so it's not ready yet. So it's easier to show it here. But the ideal case would be that you want to display something and you do tessellation at some point. So I'm using built-in for that reason. So I'm going to create a new shader, the surface shader, and I'm going to call it, let's say, example for now. So let me just bring this outside. Okay. I'm going to open it. Let me dock it here. So it's a very basic shader. Right now it doesn't have anything. And let's just start by doing some displacement first. So I'm going to place this on a plane, a new plane. Let me just select these and hide them for now.
And I just realized I was muted.
Oh.
I was saying, so Patrick is mentioning that he did a function for normal reconstruction.
Yeah.
I was just going to say, if you want to share that with us, Patrick, we accept community submissions.
Just to say that the you can actually do simple normal reconstructions with shader functions. However, the most complex ones, you can't do a shader function with them because they depend on the way you do the displacement, which is something that is different from shader to shader. So you can't do a shader function with it because it's always different. Okay, so I have this plane. I'm going to assign my material. And I'm going to, so you can see it better, I'm going to place a color nodes. I'm using some yellow to represent sand, but it could be anything.
Oh yeah, Patrick, I remember that flow shader. I believe there was a reason why we didn't include it, but we did check it out. I'll have to check, but I think we had our own flow.
Yeah,
flow map example.
I actually have like a flow map shader function prepared already. I think I never released it for some reason. I can't remember which was. I think I was waiting for an update to the editor.
Yeah, it was a while back.
Feature. Yeah, I can't remember what was the case right now. Okay, so we have a plane, and I'm going to displace it. Let me just change the smoothness of this just to get some nice highlights. Okay, so I'm going to create a displacement. You do this by changing the offsets of the vertices, and usually you do using the vertex normal. So you could just simply move the vertices to one direction that you want, but because usually these kind of shaders go to a mesh that is not a single plane, so it has like mountains and wherever. We want to displace it accordingly to the normal and not just up or down or left or right. So by what we need to do is to use the vertex normal, and we need to multiply it by a value. So let's call it displacement for now.
Mm-hmm.
And let's say 0.2, and we're going to multiply it and just plug it on the local vertex offset port. Okay, so when I do this, when I now change the displacement, the only thing that will happen is that the object will start to float a little bit higher. That's because the only thing it's doing right now is just changing according to the normal, and the normal is just pointing up right now. So that's why it's only doing this. But what we want to do is to change according to, let's say, a texture.
Yeah.
That's the most common case. So let's place a texture here. Let's call it height map.
Hey Jake, welcome.
And we simply multiply it. So let's multiply just the red channel.
So just the most basic displacement.
Yeah, this is the most basic displacement case you can possibly find. And I'm going to find my sand height map. You can see it right here, but yeah. Okay, so it's you can find this texture on our asset folders. So
Yeah, part of our samples.
exactly. So now when I do the displacement, you can see that only some parts of the actual plane actually change. I'm going to increase so that you can see. I'm going to increase the displacement here.
Patrick says he always uses green or blue. Is it
For
because of
the color?
On the texture? Is it because of compression?
Yeah, that's actually a good point. Usually the green and alpha channels are the ones that have a higher compression. Let's say not a higher compression, a higher bit count for the compression that it's done.
Yeah.
It depends on the kind of the compression that you set up on your texture settings. Currently, it doesn't really matter for now, but yeah, it's usually a good, let's say, a good practice to use either the green channel or the alpha channel.
Cool.
In some cases, for example, the way things are compressed, the red channel only has 5 bits, the green channel has 6, and the blue channel has 5 as well. So you use the green channel because it has 1 bit extra. So that's the reason.
Cool.
Okay, so now you can see that some vertices are being displaced, but you can hardly see it in this case because if you now change to the shaded wireframe mode, you can see that some vertices are higher than others, but because the mesh is really not dense at all,
yeah.
we can't really check the other thing. So I'm going to just turn on tessellation for now, just so we can get a nice view. I'm going to change it to fixed, and 15 should be fine. Okay. So now you can see that we are displacing according to the texture.
Mm-hmm.
The shadows are hitting or let's say the shadows are being rendered on the correct side. However, you can't tell any lighting information. In fact, if I went to the mesh renderer and disable the casting of the shadows, you couldn't see anything at all. So it still looks like the flat plane. So the most basic kind of way to fix this is to simply use a normal map. And in this case, we actually have a normal map for this asset. So I don't only have the height map. I actually do have a normal map as well for the sand. So if I now search it, I have a normal map. If I plug it in on the normal here, you can see that instantly you get a good looking result. So now the lighting is working correctly. So this is probably the most basic way to fix displacement, is to simply use a displacement, a normal map. However, there's 2 things that are important here, which is you don't always have a normal map available to you. And the other one is that you don't even, sometimes when you do this displacement, you don't even use textures at all. So that's what we are going to explore today. It's the way you can fix this issue when you don't have these textures, and what's the difference between them and what you need to pay attention to. So this is the most basic setup for correcting the normals. They are not being reconstructed here. They are only being rewritten because of the normal map. But we need to be able to at least create some normal maps or some normal information from height maps or some other kind of displacement that we do. So let's let's leave this here and create a new shader just so we can compare the results.
Awesome.
So I'm going to duplicate this, and I'm going to duplicate the example as well. Okay, so I'm going to call it reconstruction for now.
Hey Patrick, how's your tutorial series coming along?
Okay. Okay, so I'll wait for, well, I'll keep going and then.
Oh yeah.
Okay, so I just duplicated the shader and the material, just so we can keep the other one just to compare the results. And I'm now going to delete the normal map, just to remember this is what happens if you don't use any normal map. And now let's try to come up with a solution for the normals here. Okay, so we already have one really basic one that it's not, let's say that it does something already, and you could, if you don't know how to do anything at all, this would be like a really quick solution if you're just starting with shaders, which is we have a shader function called normal create. This was actually was created by the Unity already has one like this on shader graph, so we just try to replicate it here so that users could use the ones that they have on shader graph. So in this case, I'm going to just use the normal create. You can see that it has like an output of a vector3, and it's actually asking for a texture and some UVs. What this does is, if we use a height map here, it will try to transform the height map for it'll try to transform the height map into a normal map. Oh, we have Hippocoder here in the chat.
We have what?
Hippocoder, from the forums of Unity, the moderator.
I think mine is a little bit delayed. Welcome.
Okay, so in this case, this is the most basic way to solve the issue, which is to just use a texture object instead of a texture sample. This is just a reference to the height map. I'm going to select my send height map here. I'm just going to connect it there and connect it to the normal output. This would be like the most common way to solve it, which you can see that it does generate something. You can see that they are not exactly the same. So the normal here is not exactly the same from the normal map that we had. The reason, or not the reason, but the way this normal create shader function was created, it's done in a way that it tries to be quick and efficient, but it does produce some errors. So what we are going to do is that we are going to basically recreate this normal create shader function from scratch, and we are going to do it the correct way, and we'll see that the result will be much closer than what we are getting right now. But I just wanted to show you this shader function only so that you could, for example, if you have like a little time to work on this solution, just use this shader function, and you have like at least something to work with from the get-go. So, okay, so let's forget this shader function, and just let's try to create it from scratch in the proper way. So I'm going to delete this, and I'm going to create 4 texture samples. Okay. So what these 4 texture samples are going to do is we are going to create like an offset to the height map, and this offset will try to change the sampling of the height map on the x-axis and on the y-axis. And what we are going to do is then try to see the difference between the very small offsets, and that will give us like a variation, or like a slope of the height map. And we need 4 because we need to displace or offset the height map on the x-axis for the left and for the right side. And then we do the same thing for the y-axis on the bottom and up side. So we need 4 because this is going to be the left side, and this is going to be the right side. This is going to be this one is going to be the bottom and the top. And what we are going to do is going to resample the same texture. And I'm going to use like a small trick here, which is all of our texture samples can reference another one. So you don't have to use the texture object to reference which texture you want to use. So I'm just going to change my samplers to reference, and I'm going to reference the height map. I'm even going to delete this and copy again, just to make it faster. Okay. And let me just try to, I have like my sheet guide here, so just forget about this. I'm going to use it as a guide for me. So like I said, we are going to offset the UVs. So we'll use the texture coordinates node to do that. And we are going to reference the height map as well on the texture coordinates. And we are going to offset the UVs by a really small amount. I'm going to call this small amount the deviation. And so I'm going to create like a simple property which we are going to use to change this deviation in real time in the material. So deviation, like maybe from 0 to 0.1. And I'm going to create a register node just to make it easier to connect this on, because this is going to be shown on multiple parts. So I'm going to call this deviation as well. And I'm going to just leave it there. And so to do an offset, we just need to add a value. But remember that we are going to do on the X and Y axis separately. So we need to first add the value on the X and then add the value on Y separately. So that means we are going to do an add for each of one of these. So in this case, let's say that this is going to add to the left of the, going to offset on the left of the height map. It is going to offset on the right. So in this case, I'm going to add a small value, which is going to be our deviation. So I'm going to use the get local var node, which I created the node by pressing G and clicking on the editor. And I'm going to select my deviation value.
Cool.
So I'm going to add this deviation to the X. However, you can see that this deviation is just a single value, and our UVs are a vector2 value. So we need to use an append node just to make sure that we only want to deviate on the X component of the offset.
Yeah.
Okay. And go ahead.
Just one quick one here. Patrick says, I think we can fake AO using channel on a normal. Oh, you're referring to the ambient occlusion comment previously. Sure, I guess you could use any information to generate that, depending
fake AO using
on what you're
channel.
going for.
The issue of using the blue channel of a normal map is that usually the blue channel is discarded on importation when you import the texture. Right. So Unity tries to use as much bits that they can from the normal map. So what they do is that they discard the blue channel and then compact or compress both the red channel and the green channel on in a higher bit count. That's why every time you need to sample a normal map, you need to unpack the normal map and you need to rescale it to a proper value. So even if you try to use the blue channel, you're not actually using it because Unity is discarding it.
Right. So Casey is also asking about references and samplers.
Mm-hmm.
So he wants to know if using references will not use up additional samplers in the shader.
Not samplers. What is going to happen is that it will reuse the sampler that is created for the original one. It's only creating additional sampling of of those samplers and textures. So it's let's say that you have like a sampler is the object that has the information that if the texture is like repeatable or clamped or bilinear filtering or point filtering. The texture is the reference to the actual assets of the texture. And by using these references, you are reusing both the texture and the sampler, but you are doing the sampling of the texture, which is going to give it's going to give us the color of the texture multiple times. That's the only thing that is going to happen when using these references. Okay, so we just added on the X side, and we'll do this as well for the Y. We could just, I said that this would be the Y and this the X. We can do it that way. It's only going to make it a little bit harder to read the graph. But the idea here is that we are going to, we're going to change, this is going to be changed on the X for the positive X. This is going to be changed, offsetted on the positive Y channel. And now we are going to negate the deviation. And we are going to do the same thing here, where we are going to deviate from the negative deviation on the X and the negative deviation on the Y. And I'm just going to connect these as well. Okay. And connect here. So just to remember what it's going to happen, if I now change the deviation, you can see that some textures move around. So let's see here. So this one is moving to the right. So sorry, to the left. The bottom one is moving to the bottom. And in this case, this one is moving to the right. So 0 moving to the right. And this one is moving up. Okay. So far, so good. What we are going to do now is that we are going to make something which is simply to do, but maybe hard to understand. What we are going to do is to save some instructions by appending the values together, which is I could simply use a subtract node and try to subtract the X, the positive X and the negative X, and do the same thing for the subtract on the Y channel. However, I guess a smarter way to do would be to first append these two.
So you're just basically offsetting, right?
Yeah, I'm offsetting the texture to the left and to the right, up and down, just by a small amount.
You were right, Patrick.
Yeah, it's yeah. We can call it offset if you want.
No,
The deviation, yeah. A posh name.
Sounds good.
Sorry. Okay, so instead of doing two subtracts, we are just going to do one, because I append both the X and Y. So by doing this, the subtract is going to happen on both channels at the same time. So we are saving an instruction here. We are probably not saving, though, an instruction on the append, but it happens to be the same, and this gets the graph a little bit more cleaner. I think this actually I think we want to do on so this is going to the right, this is going to the left, so we want to actually change the order of these connections. So just remember, the way I change these is by holding control. So if I hold control and change the connection switch.
Very useful.
And now what we have here is that we have like a, you can think of it like a normal map, but only on the X and Y channels. We still miss the blue channel for the normal map that we usually call a normal map. In fact, if I use the normal map that I had previously added to the other example, if I deselect the blue channel, you can see that it's kind of similar.
Yeah.
Where is the okay, the deviation? So if I change change it to a small amount, you can see that it's almost the same. Okay. So we only need to recalculate or reconstruct the blue channel. And the way we do this, the way that it's mathematically correct to do this, is to simply think of it like a vector. So when we have a vector, a unitary vector only has a length of 1. And so we have 2 channels here. So we need to do some math behind it in order to recalculate the z-axis or the z component of the vector. It's a little bit math intensive. It's just actually just 4 nodes, but you might get lost with it. So just bear with me for a moment here. We do this by doing dot product first.
I know that.
And we do a saturate then.
I'm sure you'll make it look easy.
You can see that the dot product creates like a weird black and white effect here. We clamp it between 0 and 1 with the saturate node, and then we invert the selection, and then we do square root, and this would be our blue channel. So this is the recalculated blue channel that we were missing before. So in this case, in order to get the final normal map, the only thing that we need to do is to append the recalculated z component to the other 2, and we have our normal map. Okay. So if I now use this on my normal input here, let's see what we get. Okay, so it's not as janky as before. I'm going to compare it to the normal create again. I actually deleted, shouldn't have deleted, but sorry, not this one. Okay. Let me just find my texture again. And I'm going to compare it using a static node, just so you can toggle between the 2 of them. Okay, so this is the, sorry, let me just switch here. Okay, so this is the normal create result, and this is our result. So you can see they are different. You could say that, for example, the normal create actually looks a little bit more like sand, but that's not the point here. The point is that it's not really correct. So you can see that they are different.
Yeah, I think the compression kind of kills it, but they can check it later when we share a sample of the shader.
Okay, let me just try to...
But we can see some difference, at least on my side. I hope the stream, I hope it's noticeable.
I'm trying to get it bigger so you can see the differences.
Yeah, I can see it now.
Especially in the, this is the one that uses the normal map.
Mm-hmm.
If you see the connection here, this one doesn't align at all. you can see the highlights are really misaligned. This one, you can see it's softer, but it actually aligns correctly.
Yeah, there's a big difference.
Okay, so this would be the proper way of doing the reconstruction of the normal using the height map. However,
sorry, one
real
Go quick. Patrick is asking if you can put an int on the Z normal reconstructed. Perhaps you.
An int 1. Oh, you mean like a value of 1?
Yes.
I could, but that would mean that the reconstruction was not correct, because what we want to do, we want to find out the final piece of the vector, and when you have like let's say you have a vector, a unitary vector that has a length of 1. When you have the x and the y component, you can, because you know the length is 1, you can find out the z component. If you just use like a arbitrary value of 1 on the z component, you are making it the length of higher than 1. So you would then need to do a normalize, and it would not give you the same result. I can actually show it here. So I'm going to add a normalize here, and I'm going to simply put a value of 1 on the z-axis, which is what Patrick is suggesting. And I'm going to compile it and check the result again. In fact, I'm going to change my static switch here, and I'm going to just check the differences between using the value of 1 and using the proper recalculated value. So something like this. Okay. So yeah, it's probably you probably can't notice all that well, but this is without. Well, no, this is with the value of 1, and this is the proper recalculation.
Yeah,
you can see that it's getting darker, but it's a small difference here. Maybe in this case it's small, in the other case would be a much higher difference. You could, I guess it's possible to say that you could use the value of 1 as like a fast way of doing it. So if you want to save on some instructions, you could simply use the value of 1 and save a little bit. Well, in this case, it would save all these 4 nodes of instructions. So yeah, yeah, in this case it's barely noticeable. Yeah, you can see just like a small highlight or darkness showing up, but yeah.
Patrick mentions maybe for a LOD.
Yeah, sure.
Yeah.
You could have like on the closest slot, you could use the proper one, and on the farthest slot you could use the approximated one, I guess.
Cool.
Okay. So let's move on. Let me just delete this. And now we need to, okay. Let me just regroup these ones. And in fact, I'm going to create a new register node here. I'm going to call it my, my normal reconstruction.
Hey Andrew, welcome. We don't have an hotkey to connect anything to the debug input, but we're actually looking into adding something that's going to make it easier to preview any connection to the debug input. So
yeah, what we want to do is to be able to mark one of these inputs. Let's say that you wanted to mark the debug input, like a hotkey to mark it, and then use another hotkey somewhere. Let's say I wanted to debug this part of the code. I would then use another hotkey which would connect this output into the other input that was marked previously. That's the idea. And then you could just switch between the ones that you wanted to, instead of reconnecting, I guess, every time.
Yeah.
Okay, so I just used the register local node here, and I created a get local var with the normal reconstruction on the normal. Okay, so this would be a better way to reconstruct. However, this could still be a bit heavy in terms of shader performance. And the another way we could do this is to actually reconstruct the normal on the vertex side, meaning you, instead of reconstructing on the fragment side, on the pixel value, let's say, you reconstruct the normal on the vertex function, which is the function that analyzes each vertices and recalculates the position of those vertices. So we would instead calculate the normals and override the normals that come from the vertex function. And we do have an output here that's called the local vertex normal. And what I'm suggesting now is that we, instead of using this normal in the normal output, which is on the fragment, is to somehow use it on the local vertex normal here. If I just use it directly like this, you'll see that it's not going to do what we want. It's really strange looking, okay? And the reason is what we ended up calculating here below is just a normal map. And if you can recall, or if you understand what normal maps are, they are tangent-based information from the mesh, or in this case, for this plane. So it's in tangent space, let's say it that way. And this local vertex normal here is in object space. So it actually contains the normals that you see in your 3D software when you are editing the software. If you try to check the normals, it's those normals that we are supposedly trying to reconstruct here. So those are in local space, and what we have here is a normal in tangent space. So we somehow need to reconstruct this from the tangent space into the local space. It's actually fairly simple. We need to create a matrix to transform it, but the matrix is actually really simple to do. What we need here is to create a matrix that uses the three axes, in this case, of the local space for the normal, which is the normal itself, the actual original normal, and both the tangent and bitangent values, which are two other vectors that we can actually get on the shader, to recalculate or to create a matrix that contains the necessary information to transform our object into tangent space. So in this case, we need to create the matrix from vectors. This will create a matrix, and we assign 3 vectors to create that matrix from. We only need to create a 3x3 matrix in this case. And the 3 vectors are going to be the normal, the tangent, and the bitangent, all in object space. So in this case, we need to use the vertex normal node, the vertex tangent node, and the vertex bitangent, or binormal, sometimes it's referred to binormal node. And the order here, I simply decorated the order. It actually has some sense here, but it's hard to explain. It's depending on the way you see the object in space. So I usually decorate by using the acronym TBN. So T for tangent, B for bitangent, and N for normal. So it's TBN.
Hey, welcome, Caio.
And we are just going to connect these like this. Okay, so this is going to be our transformation matrix to transform this normal map here, or this normal information in tangent space, into object space. I'm going to simply create yet another register node, and I'm going to say it's object into tangents. Okay. And this object to tangent node, which is the matrix that we need to use to transform this normal map, this matrix is actually only capable, well, it's not only capable, but it's used to transform something from objects, which is the original values here, into tangent space. So what we need to do is do the opposite of that. So we need to transform from tangent to object space. And if your matrix is orthogonal, which is well, it's hard to explain. It has to do with matrices and algebra. So just think of it like if the three vectors are aligned in a way that they are perpendicular to each other, you get a orthogonal matrix, which is the case for these three vectors here. So we can do the operation by using the transpose of the operation, which is instead of using, usually when you do a matrix transformation, you do a multiply or a mul between the matrix.
Yes, Caio, we know. We actually checked just real quick. Caio also mentioned that it would be cool if this was automatic at some point. Do you think that's something that's actually usual to have?
What would be the automatic parts? The transformation or
the actual vertex?
Reconstruction?
Normal reconstruction. Yeah.
The issue with being it's automatic is that we don't know what kind of input we are doing or what kind of transformation we are doing to the offset.
Exactly. Yeah.
So in this case, I'm doing one based on a texture. So we could have like a shader function that does this, but we can't figure it out for the other cases. In fact, later today, I'm going to show you a dynamic wave, so something that changes over time, which is not a texture, doesn't use any texture at all. And in that case, we couldn't simply do any kind of automatic recalculation or reconstruction of the normal. So it would only be possible in certain cases. Oh, that recalculate normals, but that recalculated normals, that function is only for the CPU. So what they do is that they actually get the information from the adjacent vertices and try to recalculate the normals with that information. You have to keep in mind that shaders, when shaders are being evaluated, each vertices don't have the information of the ones adjacent to it. So you couldn't do this on a shader. You can recalculate in the same way that that function does on the CPU. Maybe we could do something using the geometry shaders, I guess, but only for the vertices that are part of a single triangle. So I'm not sure if it would work like smoothly like we want to do here. So carrying on, I said that usually matrices transformation are done by multiplying the matrix by the vector, which in this case is the normal reconstruction. Okay, and this would be the way you do a matrix transformation. By changing the order of the ports, we are doing the transpose operation, which in this case, because the matrix is orthogonal, is actually also the inverse operation. So just by doing this opposite connection here, or this inversion of the connection, I'm now transforming the tangent space normal into object space. So that's the only thing we need to do in order to reconnect, in order to reconstruct the normal into object space. And by doing this, we should get a proper normal. And now this normal is being recalculated in the vertex function. You can even see that we start seeing the tessellation of the mesh using the tessellation. So if I share you the wireframe, you can see that it's now being done in the vertex side. I'm going to show you the on the fragment side. So this one actually looks a little bit better, of course. However, it's more expensive, and sometimes you can live with having the normal reconstructed on the vertex side. So that's the reason why we do this matrix reconstruction this way, or this matrix calculation that way.
So is it a big difference in performance? Or
Oh yeah.
Yeah. So
you can think.
Sorry, I was just going to ask. Would you recommend using this on lower end platforms?
Oh, for sure. I mean, I guess on lower end platforms, you always need to test it out. So don't just trust my word on this. You have to do a stress test on all platforms, and you can think of it like if you are doing this reconstruction on the fragment side, you are doing the reconstruction for every single pixel on your screen. And if we are doing on the vertex side, we are doing it for every single vertex on your screen. And you can see that we have a lot less vertices on the screen that we have pixels.
Of course.
So that's why it's orders of magnitude faster doing on the vertex side. Okay. So now that we just reconnected or we just reconstructed the normal on the vertex side, and we have this matrix lying around, it's a good time to show you a proper way to do this for something that doesn't use any textures, for reconstructing normals that don't rely on a height map, let's say. So what we're going to do now is that I'm going to show you just like a simple example of a dynamic wave, and I'm going to reconstruct that wave using the same principle, but we will see that this part here is going to be a little bit different. And the only parts that we are going to keep, basically, it's going to be this part above, which is the matrix that we need to transform, and some of these parts of the normal way you do the displacement, so using the vertex normal and so on. Okay, I'm going to duplicate my shader yet again, and I'm going to rename it wave. Sorry, I'm going to rename it example wave reconstruction. And I'm going to duplicate my material as well. I wanted to give it the same. Sorry. And I'm going to duplicate my plane, and I'm going to assign my material to it. Okay. For this case, I actually till now I'm just using the regular plane that comes with Unity when you do the 3D object, create 3D objects plane. However, we are using the tessellation in order to actually have enough geometry to displace the textures. You'll see that tessellation actually does pose some problems in some cases, in some parts that you are going to test this. So instead of using the regular plane, I actually just prepared another plane that I created in Blender. The only difference is the higher tessellation. So I'm going to replace this. I'm going to, just to show you, I'm going to disconnect the, not this one, sorry. I'm using the wrong shader. So it's the example wave reconstruction. Yeah. And I'm going to disable tessellation. Wait, did I? Yeah, I messed up the materials.
No
Sorry
problem.
about that.
Guys, if you have any questions, now is the time.
Yeah.
How are you enjoying
Sorry about
the
that.
explanation so far? If you guys have any questions or if you want to go back at any time, just let us know. And of course, we also take questions about other stuff if you're interested. Doesn't need to be Vertex reconstruction specific.
We just might not have enough time, but I can still talk about
short questions.
Yeah. Okay, so this is the one I'm creating now. I disabled the tessellation. Here's the wireframe, and I'm just going to replace it by another plane that I created in Blender that only has a higher tessellation. Okay, so nothing fancy here. Only just so we could disable tessellation for now. Okay. So now let's try to make this displace, let's say, in a way that it doesn't use any textures. And I'm just going to do like a simple wave in one direction. It could be anything else. You could have like a, I don't know, maybe you want to have like a droplet and have like a wave, a circular wave or something like that. But I'm just going to do a directional wave. I guess a good use case would be people that do water shaders or ocean shaders, and they do the Gressner waves function. So that would be a cool example for that. And I'm going to, okay, so this is just to make sure I'm on the correct one. Okay. And remember, we no longer are going to need this. I'm still keeping it here just for now. We'll still are going to need this matrix here, and I'm going to encapsulate it here. And we're no longer going to use the height map texture. And I'm going to disconnect this at least for now. And we are going to do a wave in this mesh. Let me just consult my previously created wave. Sorry.
It's cool. It's live.
Yeah.
Go for it.
Okay. So we have this here. Sorry, this one. And I'm going to remove the height map. We are no longer using it. And instead of using the height map, I'm actually going to do a wave function that relies on adding a value to the position and doing either a sine function or a cosine function to do the actual wave. And we are going to need to use the vertex position node. So the vertex position node, and I'm going to select the x-axis and add a value on it. And this value will change over time. So in this case, I'm going to add a time node. So I'm going to add a value on the x-axis. And I'm either going to use a sine or a cosine. I guess we could do the cosine function. And now instead of using the texture, we are going to add this value or multiply this value on the normal. If we do this, we should get like a wave. Yeah, it's a little bit below the surface, but yeah. So it's a simple wave. We can still see. Let me change the wireframe. We can still see that we don't have any lighting information. So the vertexes the normals aren't reconstructed yet. But you can see that's a basic wave in one direction. Okay, so you can see that in this case, we no longer use any textures. Okay, even though I still have them here, but I'm not using them. And the only thing that our shader depends on right now, it's the original vertex position. So it's using the vertex position to do a cosine of the x value of the position of the vertices, which means that whatever we need to do in order to recalculate the normals, it has to depend on the only factor that is actually driving our wave, which is the vertex position. So whatever we need to do, it must rely on the vertex position. Before, what we maybe it was not apparent here, but we were relying on the UVs of the texture, because it was the UVs that drive the position or the sampling of the texture. You can think of it like this way: when you displace a texture, how does a single vertex knows if the texture has a value of 0 or 1? It knows that because of the UVs, because the UVs are actually mapping it to the texture. So you can think of it like the previous solution was depending on the UVs, and the current one is depending on the vertex position. Okay, this is important. You'll see in a moment why. But what we need to do now is we need to reconstruct the vertices or the normals using the position. And because of that, we need to do something similar to this, but instead of recalculating the sampling or recalculating the normal by using the sampling of the texture on the left side and on the right side, we are going to recalculate the position on the left side, on the right side, and then on the bottom side and on the up side. In this case, this position will be in tangent space. So before we had the creation of this tangent space normal, and right now we are going to create vectors instead of these values here. These values were already in tangent space, and we are going to create vectors in tangent space now. So not a single value, not like a single x value or a single y value. So what we need to do is to think of it like this is the original vertex position, and we are going to recalculate or calculate two other positions. They are going to be the offset on the x and the offset on the y side. Okay. Okay. So in order to in order for this to make sense, this group needs to be the actual original vertex position, and in this case, it's still not that, because you can see that we are only offsetting the position. This is not the actual position. The actual position is still being added, or it's still this value added to the original vertex position. So one change I'm going to do now is that I'm going to change my local vertex offset output into absolute mode, which is the actual position of the vertices, and I'm going to add the original vertex position here, and this should result in the same shade and the same behavior. So I'm only trying to make this whole group the original vertex position, or the original vertex position that was displaced by our calculation for the wave. Okay, I'm even going to group this using the commentary node, and I'm even going to create like a register node that says vertex position. Okay, and I'm going to use a get node and place it here. Okay, so you can remember that this was our deviation input. This is our matrix, and this is the vertex position, the modified vertex position. I call it that, modified vertex position. Okay. Now we need to calculate two other points, and the reason we need to calculate these two other points is that we are going to create two vectors in tangent space that are going to point into the x tangent space direction and into the y tangent space direction. And the reason we need 2 points is because if you remember, the way you calculate or you create a vector is by subtracting 2 points. So we are going to subtract 2 points to create a vector, and then we are going to subtract other 2 points to create the other vector. Simply, in the reason we are only needing 3 points here is because I'm going to reuse one of these points. So I think I can explain it here in kind of weird way, which is if this was my original point, I'm going to need another one that is offset on the x-axis and another one that is offset on the y-axis. And this is going to be my vector for the x-axis, and I guess this is going to be my offset, my vector on the y-axis. So we are going to need 3 points, okay? And currently our vertex position or our modified vertex position, it's this point here, okay? Does that make sense?
Yeah.
Okay.
Kind of catching up to it, but it does make sense, yes.
Okay, so now I'm going to duplicate this because we need 2 other points. Oh, sorry, wrong key. I'm going to duplicate this and I'm going to call this my, I don't know, x deviated point, I guess.
Sorry, I'm gonna have to step away for just 1 second. I'll be right back.
Go ahead. Live stuff. And I'm going to duplicate this again. And I'm going to call this the y deviated points. And I'm going to rename these register nodes because they are always all named vertex position. And I'm going to call this x deviation. And this is going to be our y deviation. And remember that what we need to do is to basically offset the points just like we did before. But in this case, we're going to offset the position. And in this case, the way we do this is by using our previously constructed matrix here. And what this does is transforms the something that is in object space into tangent space. So what we are going to do is to transform our positions on the x deviated point and the y deviated point. We're going to transform these positions into tangent space positions, and we move those positions into the x-axis a little bit, and we do the same thing for the y-axis by deviating the points in the y-axis. But we have to remember that we need them in tangent space. So you can think of it like using 2 vertex position here, and I'm going to recreate those in tangent space, okay, and change their location, and then make them in object space again. So I'm going to duplicate it so that you will see in a moment what I'm going to do. And I'm going to multiply it by our object to tangents matrix, and this will transform our position into tangent space. And now I'm going to offset this position. Sorry, not a divide. I'm going to offset this position on the x-axis in tangent space. So I'm going to use append nodes to make sure that I only deviate in the x component. And I'm going to reuse my deviation value that I was using before. So I'm going to change. So you can think of it like this is in object space. Here the position is now in tangent space, and I'm going to change that position a little bit on the x-axis by this deviation value. And now that I have this position changed, I can then change it back into object space. So I'm going to do the transpose, which in this case is also the inverse, like I explained before. because it's an orthogonal matrix, I'm going to do the opposite operation. So just by changing the order of the inputs, this is now a transpose of the transformation. And now what we have here, it's the object space vertex position that was deviated a little bit on the x-axis by doing this. Okay, does that make sense? So this is the let's say this was our original vertex position, and now we are going to replace these two nodes by this one, or by the result of this one. So Isaac is asking, yeah, we are doing a live stream. Okay, you can check out the video later, I guess. And I'll also be sharing the files. We always do share the files on our wiki. So yeah, you can check out the result for yourself and change them if you want to play with them. So yeah, so this is our change vertex position in the x value and the x-axis in tangent space. And now we are going to reconnect this one, which was the original vertex position. And I'm going to also reconnect this one, but you can see that we only need the x components. So I'm going to use a break to components nodes, and I'm going to reconnect it here. Okay. So
what I miss? I'm kidding. You've already answered everyone at.
Yes.
Oh, cool. Thanks.
Okay, so we changed the x deviated point. Okay. So now the result here is basically the same as this one. So the transformed, the modified vertex position, but this one was deviated a little bit in tangent space by a small value, which is our deviation value. Okay, so now we are going to do the same thing for the y value, or the y position, and it's not Russian. It's just it's a little bit more complicated than the previous example. So yeah, so now we are going to replace these vertex positions nodes by something similar to this. Okay, but now we are going to deviate those vertex positions a little bit to the y-axis, and I'm going to just duplicate this because it's easier. Okay, and for some reason, okay. And I'm going to, instead of now deviating my point on the x-axis, I'm going to deviate it on the y-axis. Okay. And that should be enough. Sorry. Okay. That should be enough to replace these two nodes. Remember, the reason we are replacing the vertex position nodes is because it's the vertex position that it's driving our actual wave moving. So before we had the UVs that were the smallest thing that was changing our height maps, and now we are using the vertex position. So I'm just going to reconnect this. No longer need this one, and in this one we need again the break to components nodes, and we only need the x value. Okay. Okay. So let me just delete this one, and now we have 3 points: the original one, the one that was deviated on the x-axis, and the other one that was deviated on the y-axis. And now that we have these 3 points, we can simply create 2 vectors that are going to be our new bitangent and tangent vectors. That's the reason we create these vectors, because these vectors are going to be placed on, you can think of it like they are placed on top of the surface in a way that one is pointing in this direction. So let me just maybe zoom in here. You can think of it like one is going to be pointing on this direction, and another one is going to be pointing on this direction. And by doing this, those 2 vectors will allow us to recalculate a new vector that is perpendicular to the to the surface, which is going to be our normal vector, our reconstructed normal vector. And because we did all these parts, all this stuff that we needed to, I don't know why this keeps happening. Okay, for some reason. Sorry about that. My previews are breaking up for some reason.
Good to know that turning it off and on again works. That's always good.
And now we are going to recalculate the normal vector. So we still need the two vectors. We only have 3 points, but like I said, it's an actual easy step, because to create a vector, we only need to subtract 2 points. So we are going to subtract 2 points. So I'm going to do it, sorry, not the divide, subtract. And I'm going to subtract the x deviation by the original vertex position. So this is the x deviation position, and this is the original vertex position, or the original modified vertex position. Well, doesn't show anything useful here, but you'll see in a moment why. And this is going to be our first vector, and our second vector is going to be the same as this one, but it's going to be the instead of the x deviation, is going to be the y deviation. So you can this one will be like the tangent vector, and this will be the bitangent vector, or this is bitangent, and this is the tangent one. I can't remember right now. But now we have these two vectors. The only thing we need to do to create the normal vector is to do a cross product. So a cross product between these two. If I'm not mistaken, I think it's the order is important. If I'm not mistaken, it's this one first and this one second. Let me consult on my already created shader. Yeah, that's the correct one. And we can normalize afterwards. You probably shouldn't, you don't need to, but it's always a good idea. Crosslink. Okay. And now we have these two, you can think now this normalized vector here is going to be our final normal vector. And now this final normal vector is already in object space. So we don't need to do that final multiplication that we had to do before to transform it in object space, because it's already in object space. Because all of these points were already in object space. We only reuse the matrix in order to transform the points from object to tangent, just to do the actual deviation or the actual offset in the x direction and the y direction. But we then change it back into object space. And yeah, this should be, if everything is correct, let me change this to shaded mode. And now I'm going to connect the result here into the local vertex normal. And yeah, it worked.
Nice. Very nice.
We can now change our deviation factor to make it a little bit, so if you use like a really small value, you can see that it doesn't have enough information to decide the correct normal or the correct direction, but you can change it in a way that it smooths a little bit the result, but it gets the proper value. Yep. So something like this one, and the value can never be 0, because if it gets zeroed out, it means that it doesn't do any deviation. And when you do the subtract here, you are basically subtracting the value by itself, so it becomes 0 and it becomes black. So it could be a good idea to change the original deviation value in order to make the minimum value like 0, 0, 1, I guess. So it doesn't never touches the 0 value.
It's a good idea.
So yeah, this should be the reconstructed vertex normal for something that doesn't even uses textures. So you can see that responding to the previous question, we couldn't do this automatically because you can see that it changes by the type of modified vertex position you are doing. So before we were using a texture, but now we are doing like a cosine wave function using the vertex position, and this position could be something else. And if we use like something else, we will also need to do something else on these 2 points. So it will be always different in every case. So yeah, this is the
Awesome.
reconstructed
Yeah, I think a
vertex
lot.
normal.
Yeah, I think a lot of our users will find this very useful. This keeps coming up as one of the common questions we get. So yeah, I think this video.
People that want to do like a simple tessellation shader, they usually end up with this problem.
Yeah.
We could turn on tessellation now, just to check out the results. Where is it? It only gets smoother, but I guess, yeah, it doesn't change much. Yeah, it's too many vertices, but yeah. We actually have already a sample that does this, and that sample is the waving flag sample, and it's really similar to this. There's only some issues with it, which is it might not be explaining what's happening, and it actually uses shader functions to try to minimize these parts here. But I guess it ends up being more complex on the eye than you actually seeing it's being done. For example, if let's say that I wanted to change this wave function to have like a frequency value here, that you want to change the frequency of the wave, it's actually really simple. You only need to multiply the original vertex position by a value, let's say like a value that you can change in the material. So let's say frequency. So something like this. However, because we need to, we want to change the frequency on the modified vertex position, we also need to do the same thing for the X and Y points. And so we need to multiply this vertex position by this frequency. And remember that this vertex position is basically this one. So the one that comes here and changes before adding the time value. So in this case, I would need to multiply my value somewhere around here and reuse, let me just pull this back, and reuse this frequency here and do the same thing on the other one. And by doing this, if I now save it, I should see a new frequency value here. If I now change this frequency, you can see that I can now change the frequency of the waves.
Cool. Patrick asks if you just do the same deformation on vertex normal and pass, what happens? Not sure I understand.
If you do the same deformation
on vertex normal? And
you mean like same deformation, what, like doing this deformation but for the vertex normal? Is that what you mean, Patrick?
I think we have a little bit of lag. Oh, yes.
Okay. You can think of it like this. When you calculate this wave function, you use the vertex position to calculate the modified version of the wave. You could theoretically try to replicate it using some other transformation or some other calculation that replicates the transformation for the normal. However, it's not the same one. It's probably something that you could try to solve mathematically and find out which function it is. Usually when people end up with that solution, we call it an analytical solution. So you basically analyze the original function and you try to come up with another function that solves your problem for the vertex normal. But it's harder to do. You had to do some math heavy calculations on paper and then try to translate that math into the editor. It's possible, yes. It's just more difficult and you may end up having a lot of instructions just for recalculating the vertex normal in the same way that we already have here. So you may not end up having like um, a benefit from using it.
Cool.
So when I rotate it using a vertex solid object, I don't recalculate normal. When I rotate using a vertex solid, you mean when you just rotate the object and you don't do any vertex transformation? Or when your vertex transformation is moving all the points, rotating around something or some point? Is that what you mean?
Yeah, I think he's referring to the engine sample you did a while back. And the engine effect. I don't know if you remember that one. It was like animated.
I remember that. Yeah, that works only because, like a fan, yeah. I think it was like a plane motor, right?
Yeah, something like that.
Okay, so the reason why that works is because you are moving all the vertices around in the same fashion. So you can, let's say that my vertex modification here was moving the plane around, so it was moving everything about the plane in the same way. Then the vertex normal would need to be changed. It wouldn't need to be recalculated because all the points were originally on the same place already in object space. I know that you can see them in a different position in world space, but the object space information is still the same. The normals are dependent on the actual differences between the vertices, and the only way you need to recalculate, or the only time you need to recalculate the normals, is when you move the vertices in a way that some vertices are changed and another aren't, or if some are changed in a place that others are changed in another one. So in that case, all your vertices are moving to in the same fashion. Which is not the case of this wave function. Yeah, it's kind of hard to explain actually. It's if you use if you think like a cube, a single cube. Let me just pull the cube here. You can think of all these different faces have normals pointing outwards, right? So if you if you rotate the object, even if you are seeing the points of the object moving around, all of them are still in the same position relative to itself, because the object space position never changed, and so the normals are still following it like they usually do. So that's why you don't need to recalculate in this case. I know this is just a crude example because I'm just rotating around in Unity, not in Shader, but it's just to explain the same behavior.
Cool. Thanks for
Hope that
explaining
helps.
it. I think so. Yes, thanks, says Patrick. If you have any other questions, just go for it.
Yeah, go ahead.
Do you have anything else you want to show us, Paulo, or does this conclude the tutorial?
Yeah, at least for this tutorial, this concludes it. I'm now working on bringing tessellation to scriptural rendering pipeline, so you can, I guess, wait for it. At least for the universal rendering pipeline, which will be the first one to have it.
Yeah, that's going to be cool to finally have tessellation. It's also something people ask for a lot.
Yeah. Especially because in these cases they usually use tessellation already, so they try to replicate this effect in universal rendering pipeline, and they can't.
Yeah.
So I'm going to bring that to them.
Awesome. So if we don't have any more questions, maybe we're going to call it a day. Do you guys have anything else you want to talk about?
Now it's the time. Don't forget to hit like and subscribe.
Oh yeah.
For future videos. So.
And if you're looking for a good optimization solution, don't forget to check our Amplify Imposter solution, which is 50% off at the moment during the spring sale.
Yeah.
And of course, also Amplify Shader Editor, but I suspect that most of you already have it.
Yeah, most likely. So yeah, just keep the questions coming. And I guess I'll try to come up with another tutorial like this for the next stream.
Yeah. So we're gonna share these examples, right?
Yeah, I actually said it when you're off screen. I'm going to share this file, not these exact ones. I actually have other ones that I already had prepared. They are more concise and have
Sorry,
more.
I got the camera. I got the video in front of the preview.
I'm going to share these and
cool.
Yeah.
Yeah, so we'll put that in the video description and in the wiki. So if you guys want to check it out, just give us a couple of minutes and we'll update the stream file. It takes a couple of minutes, so it'll be up soon. And yeah, it was cool to stream again. Hopefully next time we can do this at the office, but I doubt it. So we'll see how things go.
Yeah. So yeah.
Awesome. Okay. So let me just open up the controls. Sorry, this is a bit of a mess today. Okay, so yeah, we're good to go. Thanks for watching, guys. And like Paulo said, don't forget to subscribe. See ya. Bye.
See you, people.